What's up, guys? I'm waiting on my chicken to finish cooking, and I thought I would give a quick rundown of how you can create a synchronous mod 6 counter. I don't know how well this tutorial is going to go because I just got a piece of paper with me here and some scribbling on it, but I'm going to try to explain everything. So first off, we want a count sequence in binary that goes from 0 to 5. So there are 6 states, 0, 1, 2, 3, 4, and 5, and then it repeats. And so what we're going to do first is we're going to create a diagram that goes through that count sequence within binary. So our first state is 0, 0, 0, representing 0. Then we're going to go 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, and finally 1, 0, 1. And all of these different states are binary representations of the count that's shown over here. So if you remember, binary is a base 2. So in our first position, we have 2 to the power of 0, which is representing 1, 2 to the power of 1 in our next position, which represents 2, and 2 to the 2, which represents 4. So the max count that we can have for something like this, if we filled every position with 1, is 4 plus 2 plus 1, so we could have a 7. So after you've created this state diagram, because it's a synchronous counter, it means the clock is tied to all of the inputs on the D flip-flop. So whenever the clock rises, all of the flip-flops that are attached to that clock are going to do something, depending on the state that is sent into pin D. So what we can do is create a flip-flop truth table for the D flip-flop, and we can see here that the clock on a rising edge triggers some action. So if the signal on D is low or a 0, then the output of the flip-flop, the Q, is also going to be 0. And if it's the other way around, so D is high, so the signal going into the flip-flop is high, then the output when that clock goes positive is going to be 1. So we can also think about flip-flops and the fact that each single flip-flop can hold 2 states. It's either a low state or a high state that it holds, a 0 or 1. And since we need 3, we need to count up to 5, so there's 6 states. We're going to need 3 flip-flops, 1 for each state, right? So moving on, we can create a present state, next state table. So basically what we're going to do is, because we have 3 flip-flops, each with Q outs and D ins, we have our D2, which is going to be our most significant bit, Q2. This is the one that's going to oscillate the most slowly. So the reason it's called most significant bit is because of its oscillation period as well, I believe, as well as the weight that it adds to the number that we are counting, right? So if you increment Q2 to a 1, it's going to cause the biggest change within the decimal number. So if you change 0 to a 1 and you leave the rest as zeros, that's only going to increment the number by +1. But if you were to change Q2, then you're incrementing the number by 4, which is a heavier weight. So that's the most significant bit. So what we'll do here is, in our present state section, we write out the states that we have come up with in section 1 here. So first we have 0, 0, 0, and then 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, and 1, 0, 1. And all of these correspond to what we've created in step 1 for the sequence that we want. And then the next state is literally the next state based off of the present state. So if our present state is 0, 0, 0, we want to move to 0, 0, 1. So what we're going to do is we're going to write 0, 0, 1 in our table here at each corresponding input for each flip-flop. And we're going to do that all the way down the table. So if we were at 0, 0, 1, we want to move to 0, 1, 0. So we write 0, 1, 0 in here, and we continue all the way through. And then the D input section is going to be the same as the next state section. So we just copy this over here. And then what we can do is we can move on to creating step 4. We create K maps, and we can basically derive the Boolean expression for each D input based off of the table we have created up here. This is a little tricky to wrap your head around at first, but once you get it, it's pretty straightforward. So the table here is 1, 2, 3, 4, 5, 6, 7, 8, right? And that is because with the number of bits we have, there are 8 possibilities, right? We can have 0, 0, 0, 0, 0, 1, 0, 1, 0, blah, blah, blah. We can go all the way through, and 2 to the power of 3, because we have 3 flip-flops holding each state, is going to give us 8. So 2 to the power of 3 is 8. So there are 8 possible states. So we can create 8 sections here to fill out. Then what we're going to do is we're going to have the Q2 and Q1 written up here and Q0 over here. So these numbers here on the outside of the K map correlate to the present state. So 0, 0, 0 here correlates to the present state 0, 0, 0. The stuff we have inside here correlates to where we want to go. So if we have 0, 0, 0, and we're looking, this is for one individual flip-flop, for the D0 input on one flip-flop, which correlates to if this was D0, this would be the output Q0 for that flip-flop. So we're just focusing on one bit at a time. And so if we are at 0, 0, 0, and we want to move, we're at 0, 0, 0, for Q0, because we're only focusing on the Q0 bit, we look to see what the next state of Q0 is going to be. And the next state of Q0 is 1. So we fill out a 1 here. Now at 0, 1, 0, so 0, 1, 0, we look again at the Q0 bit, and we move over and we see that it changes from a 0 to a 1. So we fill a 1 out in the table. Now we look for 1, 1, 0, which 1, 1, 0 is going to be, this is a high and this is a high. So that would represent, and this is low, that would represent a 6. We don't have 6 in our count, right? So we don't care about it. So in that situation, we just put an X here. That's for don't care. And then we do it again. We look 1, 0, 0 as the present state. So 1, 0, 0, and Q0 changes to 1, right? So we fill that out, and then we do it again. Well, 0, 0, 1, 0, 0, 1 is here. Well, what happens to Q0? It changes to 0. So we put a 0 in here. And we do that for everything within the table. And once we have done that, we can use our grouping knowledge to group elements that are high together. So in this case, this is a don't care, so we could claim it as a 1. And then this is high. These are all high. So we can group these 4 together. And when we circle that, what we can do is we can look to the bits within the present state and see which ones change and which ones stay the same. So Q2 here, if we move down, because we've grouped this whole section, as we move down Q2, we notice that it changes from 0 to a 1 down here and up here. So we're going to get rid of Q2. Again, Q1 changes from a 0 to a 1, and then a 1 to a 0 within this vertical transition or grouping here. So we get rid of it. The only bit that stays in a single state is Q0. So Q0 is low here, it's a 0. So what we're going to do is we're going to put a bar up above Q0. So that flips the input because we want the output to be true in this case. So we do that and we derive the Boolean expression for the input of D0 on the first flip-flop, and it is an inverted Q0. And then we continue on and do that for the other two bits. So I'll show you them here and you can look at what I've done. So basically we did the same thing as before. We come up with a grouping here because you can't group zeros together. You can't group lows. You can group ones and don't cares. There's wrapping rules and these types of things. You should review that if you need to. And we can say every time basically you group something together, you end up getting rid of one Q. So here we've grouped something, so we're going to get rid of a Q. In this case, we grouped one thing, two things, so we're getting rid of two Qs, which is why we only have Q0. In this case, we've only grouped one thing, so we're only getting rid of one of these Qs here. So for D1, we look at this again. We notice that Q2 here changes from a 0 to a 1, so we get rid of it. Q1 stays high, and we want it to be high, so we keep it. And then Q0, again, same column, is a low, and we want it to be a high, so we group it as an AND expression with that Q1, and we bar it to make the low into a high. And then we have another piece here, which we use the OR to add it on to this expression. And we notice that because, you know, it's by itself, we haven't grouped it with anything, it's going to be all three bits. So in this situation, Q2 and Q1 are both zeros, so we need to make them high. So we invert them. And then Q0 happens to be high, so we group it together with Q2 and Q1 bar as this expression here. So this means that there's going to be an OR gate with two inputs, and there's going to be an AND gate with, there's going to be two AND gates. One of them is going to have two inputs, Q1 and Q0 bar, and the other AND gate is going to have three inputs. So it's going to have Q2 bar, Q1 bar, and Q0 bar, or Q0, sorry, by itself as an input. And then the same thing again for D2. So if you want to pause the video as I shake here, which is really fun because I'm hungry, yeah, take a second to figure out what I did here and figure out how to derive the expression for that. It's basically the exact same process. So once that's finished, we move on to the finalized design. So we have, again, the Boolean expressions up here. You can use, oh, what the hell is the law called where you concatenate or shrink, essentially, not concatenate. Yeah, you shrink the expression using, I had his name in my head earlier, but I can't remember it now. Anyways, there's a law that you can use with these expressions to shrink them into like less gates, basically, and make the design more efficient. So look that up. Anyways, so here's the finalized drawing. So we can see that for Q0, this is the D0 bit, first flip-flop. We use the NOT signal, the inverted signal, and we pass it back into D0. So that's the only thing going into D0 is this Q0 bit. The clock is synced to all of the flip-flops within the design, the clock input, so that every time, you know, it's synchronous, the clock rises, every one of these flip-flops is triggered. De Morgan's theorem, there you go, look that up. Thank you, brain. And then your reset is tied to this inverted pin here. We're not going to worry about that. Not really using that. And then this is a disaster here in terms of the drawing, but you can see the expression I've created here holds true for D1. So we have Q1 coming out. It is inverted. Q1 invert, right? So this is the 3 input flip-flop. We have Q0 before it's inverted, comes along here. Oh my God, so fun. Q0 pops into this AND gate. Holy cow, right? 1, 2, and then Q2 inverted, which comes out here, it inverts, it connects into this AND gate. Those are all evaluated alongside Q1 and Q0 bar in another AND gate. So, and Q, where the hell am I going here? Oh yeah, here we go. I've lost myself, but you can see what I'm trying to say here, right? So, and then the same thing happens along here. And once those signals are ANDed together, they're thrown into an OR gate as per the expression and thrown back into their corrective inputs. And what we can do is we can review the answer that was given for this assignment that my professor gave us. And it's the exact same as the drawing I created, except a hell of a lot nicer looking. I don't really like how he has like this Q comes out here and knots into this D, the first D0 bit input, and then this line, which is a different color. So it's, you know, for me, it's confusing because I can hold one thing in my head at a time. This is coming into here, which is the Q0 knotted as we have within this piece. So everything here holds up is basically what I'm trying to say. Hope you guys learned something, and take it easy.